Okay, I think we can get started. All right. Hi guys. Happy Monday, happy start of the week. All right. So today we're gonna learn about some reactions. Can everyone hear me? Can everyone see my screen? All right. So for today's agenda, you're gonna be learning about different reactions. So these are all with alkenes. So we have syn addition. Hold on 1 second. Sorry about this. Okay, yeah. All right, so syn addition, anti-addition, Markovnikov addition, and then AntiMarkovnikov additions. So these are all done with alkenes, and we'll show you like all the examples and how to do these. All right, so first we'll start off with talking about like what exactly happens in general with like an alkene addition. And so this is like the general pattern. So we start off with a double bond that attacks an atom on another molecule. Okay, so let's say, for example, we have something like this, right? And then it's gonna attack, and then you're gonna have like another reactant in this reaction. So let's say we have like 2 hydrogen atoms, and then it's gonna attack an atom on another molecule. And the reason why it does is because a double bond has like is electron rich, so it has the capability of like capturing like an atom. So say this happens, and then what it's going to create is an intermediate, which oftentimes is a carbocation. And so right here, this carbocation is formed. And then this intermediate is then attacked at something called an electrophilic point. So remember what electrophilic means? Which is basically like wanting a negative charge, and oftentimes it's represented by like a positively charged atom. Oh, oops, sorry, I forgot about that. Okay, and then we move, and then we have the final product. But so for the electrophilic point, so once again I said it's something that wants a negative charge, right? So here it basically here it's just this carbon right here, and then you have the final product, which would be something that looks like this. But we'll get into more about like what you'll get more comfortable with how these look, but I'm just giving you like a general overview. So, all right. And then, so alkene additions can be put into 2 different types of categories. So we have syn addition and then anti-addition. And it sort of relates to sort of like the stereochemistry of reactions. So basically with syn addition, right, we start off with atoms that add to the same face of a molecule. Oh, sorry, I forgot to add this over here, by the way. But yeah, all right. So for this type of reaction right here, if we take this double bond, and we make it, and we do alkene addition, you would see these hydrogens that would go up on top right here. So they add to the same face. And so basically they like are in the same direction. So they could also both be like, they could also both be wedges or dashes. But they both have to be like in the same direction in order for it to be like syn addition. And then for anti-addition right here, they add to different faces or opposite sides as well. So if we take a look here, so basically instead with anti-addition, we're going to see a hydrogen go up here and a hydrogen go down here. So basically they're just on opposite ends. And also the same idea where they can also be like, so one would have to be like a wedge and the other one would have to be a dash. All right. And then before we move on to going over different examples of reactions, we have to review like the stability of carbocations, because that's really important when we consider later on in reactions what like certain products or intermediates might be preferred. And so here, remember that tertiary carbocations are the most stable and that they're attached to 3 different like carbon groups. And then the least stable is the methyl carbocation because it's only attached to 3 hydrogens and nothing else. So remember, the more carbon groups the carbocation is attached to, the more stable it is. And why that matters is because certain products and intermediates are going to be easier to form based on the stability. So always keep that in mind. All right, so we can move on to our first reaction. Okay, so we have this reaction called with an alkene and then hydrogen gas and palladium and carbon. And so this reaction is normally known as a hydrogenation reaction. And then so with this, so you have hydrogen gas, and then the other key player in this is palladium over carbon. But with palladium and carbon, it's not really something you need to know like the chemistry behind. You just need to know that it's a very important catalyst. You'll learn more about like why in 3570, but just know that it's a very necessary component of this reaction, but you don't need to really like show why. It's just something you need to include in these reactions. And so when we start off with this, and then oftentimes you can see reactions in 3570, they might be written both like this way, or they could also be written with like just the alkene right here. And then they could also be just written with just a hydrogen gas and palladium over carbon over here. All right, so then to show this reaction, here. So remember what I said before about syn addition is that they will be on the same face of the molecule. And so here, they will both end up here at this top. All right, and then another thing to remember about syn addition, like I said before, is that you can draw them also both as wedges or as dashes. So I'll show you another example right here. So you see here that you can also draw them as wedges as well, as long as they are the same stereochemistry, as long as they face the same direction. All right. And then moving on to another syn addition reaction. So this one is going to be a little trickier, but basically, so it's the alkene with a hydronium ion, or alternatively also a source of like a proton and a water molecule. And so what's going, and this is also called a hydration reaction as well. So, but one thing to keep in mind that's going to be really important as we're doing this type of reaction is that you're going to have this above reaction always happening in tandem. So we have the hydronium ion disassociating into this proton. And remember from Gen Chem that this proton can come from any source of like HCl or H2SO4. So sometimes you might see that as one of the reactants in this specific reaction, but that just means like keep in mind that there's like there's a source of protons. Here, so we can start off with this alkene. And then H3 plus. And then so remember what's in addition again? We're gonna end up gonna end up right on top like this. All right, so this is what we would call like an overview of the reaction, because actually another thing that now we're gonna have to show you is how exactly does this happen like in a mechanism. So in 3570, you're gonna be asked probably in two different about this reaction in two different ways. So you could be asked like, oh, if I give you these reactants, like what is going to be the product? Or they'll ask you to draw out the mechanism, which is basically like the arrow pushing mechanism that you learned earlier. And so we'll go over that. All right, so we have here this double bond, this alkene that I showed you before. And so we're gonna start off with our reactant with the hydronium ion. Right, and then we have this plus here. And so because remember what I said before about this alkene attacking an atom, so it's going to attack one of the hydrogens because this oxygen is possibly charged. So it's okay giving up that hydrogen, because once it gives up that hydrogen, that bond that's connected, the bond that's connecting one of the hydrogens and oxygens will be kicked off and then put as a lone pair to that oxygen, making it like a neutrally charged water molecule. Start up here. And then remember there's always H's here. But yeah, and then we have a formation of our carbocation, like I said before. And so that's our intermediate. All right, so can anyone tell me, feel free to either shout it out or say it in the chat or DM me, what type of carbocation this is?
Tertiary.
Okay, so actually it's a secondary carbocation because remember right here, there's a hydrogen right here, right? So it's attached to 2 different carbon groups, but that's okay. It'll take some time getting used to it because it can be a little tricky, but it's just once you just count the number of carbon groups. So right here, like 1, let me do this in a different color. 1 and then 2, right? And then this hydrogen atom doesn't count as a carbon group. So it's only attached to 2 carbon groups. So this is a secondary carbocation. All right, and then what happens after that is this water molecule is going to come around and attack at the electrophilic point, so that we end up getting this. All right, so now we have this. We have a positively charged water molecule attached to this. And remember before what I said about this reaction always happening like in the background or like in tandem as well. So basically there's gonna be like another lone water molecule just like hanging around, and it can take one of these hydrogens so that it can push this. It can push the bond between the hydrogen and oxygen again, like before, onto the oxygen, so that's neutrally charged, so that you now have a neutrally charged hydroxyl group. So that you end up getting this. As your final product. Right here. Okay. So does anyone have any questions about what I went over? Because I went over 2 syn addition reactions, so I want to make sure that we like get this, that you guys understand this. Okay. All right. So now we're going to move on to the other set of reactions that I talked about before with anti-addition. And so here we have an alkene with bromine gas. And so this is also, this reaction can also be called a bromination reaction. And then also this reaction can also be done with chlorine gas as well. So you might also see that as a possible reactant. All right, so once again, we're going to go over the overview of this reaction, and then we'll go over deeper into a mechanistic look. So we can start off with something like this. And then we're going to add bromine gas. To get this as our final product. And then remember, so now we're talking about anti-addition. And so that means that these bromines will end up on opposite sides or opposite faces. So remember that these are going to end up right here instead. Okay, and so this is how you're going to do this in a mechanism. So we're going to start off like before with the other reactions that I've talked about. So we're going to have these bromines. And then we're going to have this double bond attack one of these bromines so that this bond gets pushed onto just one single bromine, so that now this bromine is negatively charged. And so something different is going to happen in the reactions that we've talked about before, where with the intermediate. So you're not going to actually get a carbocation intermediate at this stage. You're actually going to get something like this triangle. And this is a triangular intermediate, or it can be called a bromonium ion as well. And then remember that we have this bromine that's negatively charged from before. And okay, so you see how there are there's two different carbons, the left or the right carbon. The bromine, that negatively charged bromine right here, is actually going to prefer attacking one of the carbons over the others. Can anyone take a guess about which one it is? Think about, and for a hint, think about the stability of carbocations.
Is it going to be the carbon on the left?
Yes, exactly. Do you want to tell me why you think that? It's okay if not, though.
Because the carbon on the left is a tertiary structure, which is more stable than the right, which is a secondary structure.
Yes, exactly. Good job. Yeah, that's exactly what happens. So once again, reiterating, it's basically based on the stability of the carbocation that would be created. So obviously this one is a tertiary one. If we see here, there's 1, 2, 3 attached groups. And then this one on the right is attached to 2 groups. So that's why that bromine ion would attack the left. And so then it kicks the bond of this bromine off right here so that we get our final product. All right, so then we get this as the reaction. All right, okay. And now we're going to move on to another anti-addition problem. Okay, so an alkene with bromine gas and then water. So it's going to be similar with the reaction we did before, except instead we have to account for water in this. Okay, so here's the overview of this reaction. And then, so remember anti-addition, they're going to end up on opposite sides. So you're going to have a bromine up here or a hydroxyl down there, or vice versa. Just make sure that they're on opposite ends. All right, and then we'll go into a mechanistic study. All right, so we start off like the same like before as we've been doing in these previous reactions. So we have these 2 bromines. And then that double bond is going to attack that bromine, and then it's going to move that bond, the bond that's attaching to both the bromines, just to one bromine, so that's negatively charged. And then same thing as before, you're going to get this triangular intermediate. And then remember that we have a water molecule also as one of our reactants. And so now, like before with the bromine that was attacking, like which one is it attacking? So it's going to attack the left one like before because of stability of the carbocation, of this tertiary with carbocation. And then that's going to move that bond right there. So that now we have 3. So we're going to have this bromine on top. And then remember here, we're going to actually have a positively charged oxygen. And so what we're going to do, like we did in one of the reactions that we had water before, so we're going to have like another lone water molecule hanging around. And what it's going to do is it's going to take one of these hydrogens, or deprotonates is actually the official term, so you might hear that as well. So there's a step of deprotonating the water molecule so that this becomes a neutrally charged hydroxyl group. Sorry, this is a little messy. Let me move this a little bit, so that's like that. All right, so then this is how we got our final product from before. Okay, does anyone have any questions on anti-addition? Okay, all right. So we're gonna move on to something to consider about anti-addition. So once again, stereochemistry comes back into play. So stereochemistry is really important throughout, especially 3570, because you're gonna have to remember like what happened. You're gonna have to remember the stereochemistry of like what happens from the reactants to the products, and understanding sort of like the shift or the change between them. So here, if you remember from before when we talked about Z stereoisomers, so remember that means just the high priority groups are on the two highest priority groups are on the same side. So they're going to both end up here. And so let's do a reaction, right? So if we take Z stereoisomers, they can result in a product and it's an enantiomer. So, and remember what we learned before about enantiomers, they are mirror images, but not superimposable. All right, so we're going to do a reaction. And so we can do chlorine gas. As I mentioned before, that's a possible reaction. All right, and then here we get to this following reaction. And then we get, as I said before, we get it's an enantiomer. All right. So also for a quick check, now that you guys have learned, R and S configurations, and so taking a quick look, you can see here that this, the ones on the left both have an S configuration, and then the ones on the right both have an R configuration, and that's also how you can check if they're enantiomers or not, if their configurations are opposite, if the stereocenters are have opposite configurations. And then we have E stereoisomer. I remember with E stereoisomers, that means their two highest priority groups are on opposite sides, so, or opposite planes. So this one will be right here. And what you can get actually instead is a meso compound. Oh, oops, excuse that. All right, and then we're gonna get this meso compound. And then remember what we learned before about meso compounds. Basically, they are achiral molecules and they have an internal plane of symmetry. So meaning if you drew a mirror right in between the two, you would get them, the stereocenters would reflect the same, would be mirror images of each other. All right. And then, so one final thing to keep in mind with stereochemistry of anti-addition. So we're going to do an example with a ring because there's something that you don't really notice with the previous reactions that we've done with anti-addition. All right, so let's take this cyclopentene with this methyl group, and then we'll have a deuterium to sort of show the difference between like a high as like a tracer. Okay. And then we're going to have the bromine gas as a reaction here. Okay. And then when we draw, this reaction right here. So now we have to take into account stereochemistry. So now you need to draw your wedges and dashes. So I'm not going to show like the full arrow pushing mechanism, but just remember that an arrow pushing mechanism happens in here like before. So that means this bromine atom is going to form, the double bond is going to attack the bromine gas so that it forms the ammonium ion. And then we're going to have this water molecule come around. And what's going to do in this, it does this in all cases, but it's really important that you know it specifically in this instance with a ring. It does this thing called a backside attack, in which, so it'll attack from behind because here the bromine atom is like wedged, so it's facing towards us, right? So the water molecule is going to come in from behind, and it's going to do something. It's going to do something a little interesting. Basically, it's going to change the stereochemistry of this methyl group. So this is also called inversion of stereochemistry. But yeah, so you see here how we had, let me highlight this for you. Okay, so remember here, this methyl group was once wedges and now they, was once dashes and now they've formed wedges. Oh, sorry, I flipped these colors. Oops, sorry, this should be blue. Let me fix that. Okay. But yeah, so now we have an inversion of stereochemistry right here. So now it has changed. So that's just like a feature of anti-addition that it inverts the stereochemistry. So that's one thing to keep in mind. And why I'm saying this is because when we were doing this originally, oh, yes, there should be a positive charge. Sorry, thank you for pointing that out. Yes, you are correct. But yeah, so one thing that's a little different about doing it with a ring is that when we were doing anti-addition before, right? When we were before, we could just put the new product, we could put the bromine atoms on these on like the straight lines, so that you didn't have to worry about them. You didn't really have to worry about whether about the stereochemistry with like the wedges and dashes. But now with a ring, you're forced to look at the wedges and dashes because the straight lines are now occupied by the ring. So yeah, does anyone have any questions? Okay, I think then that's it for me.
Time for part 2. Let's see if this will work today. Awesome. Can anyone not see this? See me? Oh, see me now scribbling on the page. Nobody is saying anything, so I'm going to assume we are good. Cool. So now I'm going to talk a little bit about the Markovnikov rule and the AntiMarkovnikov rule. So these are going to be some other ways we use to classify reactions. Basically, do they follow this rule? Do they not? And so you're going to see specifically with the Markovnikov rule, Gigi actually kind of went over this without talking about the name. So as I talk about this, you should start to think, oh, like, you know, we're talking about stability. This makes sense. This is what Gigi was doing earlier. So we're going to talk about the Markovnikov rule in terms of alkene addition. Remember that in alkene, let me check my settings. In alkene, it's just going to be a double bond between carbons, maybe some other stuff is happening on the side, that kind of thing. And so with the Markovnikov rule, what we're going to see is that the product with the most stable carbocation intermediate, let me highlight that for you, is going to be preferable. And what that usually is going to mean is it's either the only or often the major product of some kind of reaction. And so we're going to do the Markovnikov rule in terms of alkene addition with a hydrogen halide. So this is going to be your hydrogen halide. The general form is going to be HX, where H, that's just a hydrogen. X is going to be a halogen. Most times you're going to see something like chlorine, bromine. I think I might have seen iodine. I can't talk a couple times. But basically what we're going to see is that the X, the halogen, is going to add to the more substituted carbon. Let me go ahead and highlight that. Substituted carbon. Remember that the more substituted carbon is going to mean the carbon with the most other carbons already attached. And then, as you might be able to guess, that means that the X for that component is going to add to the other carbon. So the carbon with the most hydrogens, in other words, the less substituted. So I'm going to say less subbed C. And so you might think, okay, that seems like, why does that happen? And remember, and I'll show you this in a second, this is going to be because this is going to form the most stable intermediate. Remember your stability of carbocations. Tertiary is going to be the most stable, going to happen most often, then secondary, then primary. So our example is going to be an alkene with HX. You could use HBr, you can use HCl, whatever you want. And so I just have the general form of an alkene here. Remember, R is going to be rest of the molecule. I did R prime 1, 2, and 3 just to show maybe, you know, this could be a 3 chain carbon. I don't know. This could be 4. Doesn't really matter. They can be different. They can be the same. And so what's going to happen? So we're adding HX. Remember, double bond's going to go to the hydrogen. Same reasons as Gigi mentioned before. This is electron rich. This not so much. And so move that single bond over because that breaks. And so we look at this hydrogen. Where do we think this guy is going to go? Feel free to say out loud. Feel free to say in chat. Do we think it's the left one? Do we think it's the right one? What do you guys think?
The right one?
Close. So thank you for those who messaged me before. The hydrogen is actually going to join his buddy on the left. And let me show you what that looks like. Remember, this X is just floating out there now. Let me put him farther away. And so let's look at this. Why does this make sense? So remember, like I said before, halogen is going to go to the more substituted C. So this is the more substituted C. It has, this is the carbon, 1, 2, 3 carbon attachments. This is the less substituted carbon, has 1, 2 carbon attachments. And so now we have created this intermediate. And let's think about this. So this carbon, the carbocation, is going to be a tertiary carbocation. Remember, 1, 2, 3 attachments. If this had been made into a carbocation, it would have been secondary because there's only 1 carbon attachment, 2 carbon attachments. So we would rather have a tertiary than a secondary carbocation because the tertiary carbocation is more stable for reasons like hyperconjugation, that kind of thing that we talked about last week. And so what's going to happen now? This is X. Halogen is now going to attach to the carbon. And so your final product is going to look something like this. And so remember, here are 2 hydrogens. Overall, the hydrogen went with, so it goes with hydrogen. So if anything to remember about this rule, hydrogen is going to go with his buddies. He's going to prefer the less substituted carbon when you're doing a Markovnikov addition. So I'm going to say for Markovnikov. I think I saw a couple questions in the chat, so let me look at those real quick. Okay, Victoria, you're good now? Cool. Any other questions on this slide so far? So last thing is you can actually, you're going to see that I drew the syn addition version of this because these are both on lines, they're both on the same side. So this is going to be the syn addition. You can also have the anti-addition for this guy. He's not selective in terms of syn or anti-addition. We'll talk about some reactions later this week that are selective in terms of syn or anti and that do or don't follow the Markovnikov rule. And that being said, we are now moving on to the anti-Markovnikov rule. And so as you can imagine, this is the exact opposite of Markovnikov. So anti-Markovnikov, opposite is going to happen. So when you have a hydrogen halide, your X is going to be added to the more substituted carbon. So now H is no longer going with his other buddy H's. He's going with the more substituted carbon. Let's do this example with an alkene. You're going to see that your anti-Markovnikov additions tend to be a little less, typical than what you'll see in orgo. Usually this will occur when you have some kind of exception. So for example, peroxide, but which we're going to say has free radicals. Remember, a radical is basically going to be an unpaired electron. So just an electron zipping around without a buddy. And this causes some complications usually when you're doing an organic chemistry reaction. I'm not going to show you the radical mechanism because it's a little bit crazy. You'll learn that in orgo. But that's going to be an important instance where you usually have anti-Markovnikov additions. So you can have a peroxide, which this is the general form. You might also see something like this or something like this. And so the general scheme for this guy is going to be a little bit different, a little bit more complicated. So we're going to have some reactant, I'm just calling it A, reacting with something, I'll just call it B. And it's going to give you some product C, but also it's an enantiomer. So let me show you what that looks like here. So we start off with our reactant. Let's go ahead and add HBr. Let's also add our peroxide. I'm just going to do this guy. I'm going to say this is a peroxide. Usually also with some kind of peroxide or free radical agent, we're going to have heat. So this means heat or light. And so let's figure out what's happening here. So where is this H going to add? Instead of going up here, which would happen with your Markovnikov addition, it's going to go down here. So bromine actually went with the less substituted carbon, hydrogen with the more. And you can have both syn and anti additions. So these are going to be both anti. I'm going to draw your two syns. Remember, these guys are just enantiomers. So just to show you where these went again, bromine up top, hydrogen on the bottom. You're going to see this is your, let's label this. These are your anti products, anti-addition products. These are your syn addition products. So remember, this is anti because bromine is on a wedge. This hydrogen we added is on a dash. And then for these guys, they're both on a wedge. They could both be on a dash, that kind of thing. And these, like I said, are going to be generally less common. Your professor and will also tell you what reactions will be anti-Markovnikov. We'll also be going over a bunch of them later in the week, so you will get a lot of practice. So next up, let's do a quick check. So here's our alkene, and let's do two different reactions with this guy. So up top, it's just going to be HCl. We can go ahead and say this is probably going to be Markovnikov. I'm just going to write Mark. Let's look down bottom, still HCl, but now we have our peroxides in our heat again. So this is going to be anti-Markovnikov. I'm going to say anti-Mark. Let's go ahead and do this. So let's talk about why this happened. Remember that here, this guy, if they're not labeled, He's going to have hydrogens. There's going to be a hydrogen here. So we want our chlorine to add to the more substituted carbon. This carbon is not attached to any others except for the other side of this double bond. This one has 2 attachments. He's going to attach to this guy. Hydrogen, on the other hand, is going to go with its buddies. And so we get this. I drew out the hydrogen just so you could, tell where it went. You can also, as you can imagine, just, oops, not like that. You can just draw it like this. Oops, not like that. Like this. There we go. Because remember, if you don't see anything here, you can know that that's just going to be a hydrogen. Usually your professor is not going to care though. So I'll just write that. Or let's go ahead and copy and paste this guy. So that or that. All right, let's go to the bottom. So if this is anti-Markovnikov, we have the opposite happening. So remember, this is the same exact structure, these two. I'm just showing the hydrogen just to show you where it went. And so you're going to see that these two look pretty different, right? So this is one instance where it's really important to know whether your reaction is going to be Markovnikov or anti-Markovnikov, because your resulting product could be like very significantly different. You're going to see here, it doesn't differ too much, but when you get into more complicated reactions, you get a little crazy. But yeah. Last but not least, let's talk about some exceptions. So the first one is going to be hydride shifts. And so remember, a hydride is just going to be hydrogen attached to some guy. So a hydride shift is going to occur when you have a tertiary carbocation. So let's say tertiary carbocation right next meaning at the adjacent carbon to a secondary carbocation, a tertiary next to a primary, or a secondary next to a primary. So you're going to see essentially what this boils down to is you have 2 different options for carbocations. And let me show you what that looks like. I'm just going to draw in hydrogens so you can visualize it a little better. Remember, you don't necessarily need them there. So let's say we have a carbocation here, no charge here. Let me go ahead and label these 2. Let's make this one blue, make this one red. So let's look at them. So the blue carbon, that is going to be what kind of carbocation? This guy attached to 1, 2 carbons. He's going to be a secondary carbocation. And let's look at this guy. Currently, he's not a carbocation, but if he were, what would he be? So he's attached to 1, 2, 3 carbons. So if he were a carbocation, it would be tertiary. So what's going to happen here is, remember, think about what stability means for this molecule. So a tertiary carbocation is going to be less stable than a secondary, yes? And so in that case, this hydrogen over here is actually going to go right on here instead. Let's just do it like this. And so this is what we call a hydride shift. Essentially, the hydrogen is, as you can imagine, just shifting over. And so now, because the leftmost, the red carbon, has lost a hydrogen, this has now formed a tertiary carbocation. This guy, he was a secondary, but now overall, this molecule is going to be more stable than this guy. So overall, this is the more stable form. And so you might see in some reactions that this intermediate is going to swap over just because it's the more stable form. Usually makes it easier to go to the final product. I'm going to show you what that looks like in a reaction. Let's go down here. Did I leave myself enough room? So let's say we start off with something like this. you're going to see this looks pretty similar to this, except currently we don't have any carbon cations. And so let's put this in a solvent. Let's put it in water. Within them here, so you don't have to draw them if you don't want. But this bromine is actually going to be a good leaving group. We're going to talk about what that means a little bit later. But for now, just bear with me. So that bromine is going to come off. You now get this. So this is going to look almost exactly, but a little bit more ugly as our example before. So you can imagine that once again, carbon in red, that would be a tertiary carbocation. This carbon in blue is currently a secondary. So this hydrogen is going to go ahead and swap over. Remember, this is still in water. You can write it in if you'd like. Remember, this bromine is still floating out here. You can draw it wherever, just don't lose track of it. And so what's actually going to happen now is that this water is going to come in to get rid of that charge. So still in water, this drawn in again. And so you're going to get something like this. And so now, in order to get rid of this charge, this is going to be a deprotonation step, a little bit like what Gigi was talking about before. This water is going to go ahead and steal hydrogen from the molecule. That single bond is going to break. And now we are going to be left with this. Oops, that's ugly. That's slightly better. Whatever, we'll go with it. Awesome. You can draw the little pairs if you want. Does not really matter. So this is going to be our final molecule. There's also, some bromine on the side. Cool. And so second example is going to be a methyl shift. And so you're also going to see that sometimes these are called, can I spell it right? Alkyl shifts. And so a methyl shift is going to be exactly what it sounds like. It's going to be a methyl group, so CH3 shifting over, a bit like a hydrogen or like a hydride shift, except, not a hydrogen. This is actually going to be a little bit more rare. It's only going to occur if you have a quaternary carbocation next to a secondary or next to a primary. And so one reason why it occurs less frequently is because hydride shifts your hydrogen is going to be a lot smaller than your methyl group. So remember, methyl group is going to be CH3 connected to something, which is R, whereas the hydride is just, little hydrogen connected to something. This guy's a lot bulkier, just a pain in the butt to move around. We're going to call that steric hindrance. You're going to hear that word a lot in orgo. So let's do an example. Okay, so let's say we had this structure. This is going to be a secondary carbocation. Remember, it's attached to 1, 2 carbon groups, so secondary. Let me go ahead and make them blue. This one red, so you can visualize. This is currently not a carbocation, but it would be quaternary if it were. And so remember, 1, 2, 3, 4 attachments. And so instead of hydride, like a little hydride moving over, it's actually going to be this entire methyl. So that's going to go slap right on there. And so this is the result of that. Note that the kind of carbocation we have or would have just changed. So this now has 3 attachments. So if this were a carbocation, it would be tertiary. This is now currently a tertiary carbocation. So you're going to see we went from having a molecule with a secondary carbocation, a little bit less stable, to having something with a tertiary carbocation, more stable. When all else fails, just think about stability. So let's do another example. Going to be pretty similar to what I did with hydride. So this guy's going to pop off. Secondary carbocation. Do that in red. Oop, I just switched the colors. There we go. Do that in blue. Do this in red. This would be quaternary. I'm going to say WB for would be. You guys know by now. This currently is secondary, not super favorable. Entire methyl group, doesn't matter which, it's going to shift over. And move that arrow. Put it there. Still in water as always. Not going to draw lone pairs because I'm lazy. You know, chlorine is still floating out here. And so we have this now. Remember, this is now tertiary carbocation. If this were a carbocation, it would also be tertiary. You can draw on a hydrogen if you want, doesn't really matter. And so now if we were to do the same deprotonation step as before, it's just going to look like the one with hydride. I'm not going to show you in the interest of time, but your final reaction, your final product rather, is going to look like this guy. Cool. Any questions on that so far? Let me check the chat. Looks like we are good. All right. So one of the last things we're going to talk about is going to be regiochemistry versus stereochemistry. So I know we went over a lot today, but I just want to illustrate an important difference between the two of these. So remember that stereochemistry is going to deal with, this is going to sound kind of dumb, but stereoisomers, as you can guess. Remember that stereoisomers are going to be different in their spatial arrangement. So when Gigi was talking about, let's do this, synate anti products before, those are terms used to describe stereochemistry. So let's just say we had some alkene here. Doesn't really matter. I'm just going to put AB. You can put, you know, HX, whatever you really want here. And so if we were to create, for example, let's say these products, and also this product, this is going to be what? Same side is going to be syn. Opposite side going to be anti. Remember, I could have put these both on wedges, both on dashes. I could have put, you know, the A on a wedge, B on a dash, that kind of thing for anti. Remember that these are going to be stereoisomers. So right, stereoisomers. Whereas in regiochemistry, that's going to deal with constitutional isomers. Remember, that's different in the carbon to which a certain element, for example, is attached. Let me show you what that looks like. So when I talked about Markovnikov and AntiMarkovnikov products, those were terms used to describe regiochemistry. So let's do the same. Oh, ugly. Same alkene. Let's put A and B on here. I'm just going to show the syn products to illustrate, you can do anti if you would like. So the difference between these two guys, ooh, that bracket, yikes. They're going to be constitutional isomers. So I'm going to say const isomers. Because you're going to see, this A is on a different carbon than this A. Maybe it has some more here, I don't know. And so remember, Markovnikov and AntiMarkovnikov, it's going to be regiochemistry, syn and anti-products, stereochemistry. So we're getting to the very tail end. Last thing we want to do is give you a little bit of advice for reactions. And so I know we talked about a lot today, but if all else fails, if you're confused about, Markovnikov versus anti-Markovnikov, or when an hydride or methyl shift occurs, it's just going to be based on what makes the most stable intermediate. Your professors will go over this like in depth, so do not worry. A lot of reactions will follow the Markovnikov rule because it's more stable. And we'll talk about exceptions like when you use peroxides or other free radicals. Hydride and methyl shifts, not as common. The professor will go over them. And sometimes, if I remember correctly, they were like, sometimes you'd have like a trick question on exam, that kind of thing, just so they can see if you remember these two. Those are going to occur to increase stability. So if all else fails, stability rules. Yeah, that is all we have for you. We'll be here for a couple more minutes if you guys have any questions, but otherwise you are free to go.
Thank you.
Thank you.
Okay, I think we are good.
Yeah,
Stop recording. Can I figure out how to stop recording? There we go.